So in the next few video lectures, we'll be talking about the source of hydraulic power, which is hydraulic pumps like this one. So to get us a feeling for how these pumps act in a real circuit, we're going to take a step out into the field and look at a log splitter application, a hydraulic log splitter. So this machine here is a log splitter, and as you can see, it generates a large amount of hydraulic force, which we use to split a log. So let me talk a little bit about the components of this log splitter. So first of all, we've got a large reservoir right here, which is contained in the axle unit, and so that carries about 15 to 20 gallons of hydraulic fluid. We then have an internal combustion engine, a gas engine in this case, which is bell housing mounted to a hydraulic pump. We'll talk more about the specific hydraulic pump later on, but it does have a built-in relief valve and another valve that we'll talk about. The high pressure fluid coming out of the hydraulic pump goes over here to a four-way, three-position valve. It's lever operated. You'll notice that it is spring return to center, but you'll notice that I did hold it in position and it returned by itself, and so it is detent operated in the return position, and then when the pressure starts to build on the return, it then pops this back to its center position. And so that is what controls the flow going one direction or the other. So from here, we'll then take a step back into the studio, and we'll talk about some of these components in more detail. All right, so now that you've seen the log splitter in action, here's the circuit for this same hydraulic log splitter. It's very similar to what we saw before when we were in the undergraduate teaching lab, where we were moving the actuator back and forth. But now this is driven by an engine, and we have a couple of other components in our circuit. So the one that I really want you to be focusing on here is the pump itself. We've seen some of these other components already. Let's focus on this pump. Now, let's classify pumps in, first of all, talking about positive displacement and non-positive displacement pumps. So positive displacement pumps, the kinematics of the pump itself determine the volumetric flow rate. So in other words, if I take this pump right here and I rotate it one revolution, it is going to give me a given amount of flow coming out of it, and that is governed by the kinematics of the pump itself. And so because of that, I can write these two equations for the flow rate, Q, in terms of the volumetric displacement, that's how much volume is passed through the pump for every revolution, multiplied by the angular velocity, and then I just have 2 pi to convert between radians and revolutions. And the same with the torque of the pump in terms of the pressure and the displacement. So these are idealized relationships between pressure and torque and flow rate and angular velocity, purely through the kinematics of the pump. Now, another classification of pumps are non-positive displacement pumps. So these would be something more like an impeller pump, where now the flow is very smooth coming out of these, but the flow rate and the torque of the pump is dependent on the pressure. And so in a positive displacement pump, such as this, if I was to block the outlet flow, the pump would stall or something would break. In a non-positive displacement pump, if I block the output flow, it'll just build up to a certain pressure, but the pump will continue to run and it will not stall the pump. So a major difference between the two. Very often, non-positive displacement pumps are used for more fluid conveyance and moving large volumes of fluid. Here we're focused more on high-pressure hydraulic systems, and in that world, positive displacement pumps are the dominant type of pump. So now that we've had a chance to talk about the circuit for this hydraulic log splitter and a little bit more about hydraulic pumps, let's examine how those pumps function in this log splitter. So I'm going to do a couple of quick experiments, if you will. The first thing I'm going to do is I'm going to start it up, and we're going to run the engine at low idle and move the cylinder back and forth. And you'll see the difference in the cylinder velocity due to the difference in the cap side versus the rod side area of this hydraulic cylinder. Next, to start really exploring what the pump's doing, I'm going to change the engine speed as we're moving. And you're going to see that the speed of the actuator, of the piston, is going to increase as the engine speed increases. As we're increasing the angular velocity of the pump, we're increasing the flow rate and therefore the speed of the cylinder. And then lastly, I'm going to explore how does the speed of the pump, or the flow rate of the pump, how is that dependent on the hydraulic pressure? And we're going to increase the hydraulic pressure by putting a log in here. So let's look at these 3 different things. So first I'm going to run this at low idle, and this is our extension speed, fairly slow. This is our retraction speed. You'll notice it's a little bit faster. And now let me run this in extension, but at a high speed. So this is our low idle, and now let me increase the engine speed and therefore the angular velocity. So you'll notice that the piston speed increased greatly. And the same thing going on in retraction. And if I increase the engine speed, it'll speed up as well. So now let's explore what happens when we increase the pressure that the hydraulic cylinder is creating on the pump. So we'll start splitting this log. You'll notice that first of all, our hydraulic cylinder is going to move at full speed, and then something's going to happen when we hit the log. You'll notice that the actuator is slowing down. So the fact that this actuator speed depended on the pressure it goes against what I just told you about positive displacement pumps. Let's take a step back into the studio and talk about why we saw the velocity of the actuator change with pressure. All right, so welcome back to the studio. Now that you saw that log splitter, you might have noticed some things that didn't quite jive with what we were originally talking about with a positive displacement pump. So first of all, what did jive is that we noticed that as we increased the engine speed, the velocity of our hydraulic cylinder increased, both in extension and in retraction. But we noticed that as the force increased, when our hydraulic cylinder started encountering the log, the velocity drastically changed. What was going on there? Remember I was saying the velocity should not change. Well, we actually had a very special type of pump, which is referred to as a two-stage pump, which looks something like this. So what is really happening here is we actually have two separate pumps. One is a low pressure, high volume pump, and this allows us to get very high velocities of our cylinder when we're not doing any real work. And then we have a high pressure, low volume pump, and this would then be used when we're actually doing the splitting of the log when we need high force requirements, or high pressure in this case. And so what's happening here with this circuit is that I've got both of these pumps are driven on a common shaft, and I've drawn my smaller pump here. This is a smaller volumetric displacement, but this would be my high pressure pump. And that is then connected to my low pressure pump. Now, both of these are driving together when we're at high velocities. They're both going out to the outlet flow. But as the pressure starts to increase, what's going to happen is this unloading valve has this pilot port coming to it. When that pressure exceeds the spring setting, it unloads the low pressure pump. So the low pressure pump just flows back to the tank, and then when that occurs, all of our flow goes from the high pressure pump, and therefore we get additional pressure at a lower velocity. You can imagine if we had to keep that high velocity, our power requirements of our engine would be too great, and we would then stall the pump. So this is one difference that you saw in the system. The other difference, if you remember when I deadheaded the cylinder, which means I moved the cylinder all the way to the end of its stroke and I kept the valve wide open. Well, what happened then was the actuator stopped moving, but the engine did not stall. Remember I said this would stall if I blocked the outlet flow. Well, the other component that we have in the circuit that takes care of this is our relief valve, and we'll be talking about relief valves later on in this course and how that functions in the circuit. But that is why this pump did not stall in that case. But again, a positive displacement pump does create a flow rate that is dependent on the angular velocity, and the pressure and torque are always balanced or always related by the kinematics of the pump itself. So from here, we'll then start talking more about how to model these pumps and the efficiency and characteristics of various pumps.